Okay, so for every other Kepler's law question we've done so far, we've used Earth as the second body. We can't use Earth here. Earth doesn't orbit Mars, okay? So I can't use Earth's information here. But Mars does have 2 moons, and they tell me, okay, the information here that Phobos is 9,378 kilometers, has an orbital period of 0.319 Earth days. So I know both pieces of information about Phobos, but I only know one piece of information about Deimos, so I can calculate its orbital radius still using this. So I'm going to have the period of Phobos squared over the radius of Phobos's orbit cubed equal to the period of Deimos divided by the radius of Deimos's orbit cubed. All right, and I'm looking for the radius of Deimos's orbit. So that'll be r d equals the cube root, okay, of the period of Deimos times the radius of Phobos's orbit, so squared and cubed, and then divide that by the period of Phobos's orbit squared. Okay, that'll give us our number. So what you can see here, guys, is that Phobos goes around Mars 3 times per day. Actually, a little bit more than 3 times per day. All right, because its orbital period is 0.3189 days. If it was 0.3 repeating, it would go around exactly 3 times a day. Okay, so it goes around a little more than 3 times a day. In fact, some of the rovers have caught it on their mast camera. Okay, you can actually see it. It looks like a potato going around because it's kind of potato shaped. Okay, the manipulation. So I multiplied both sides by the radius of Deimos cubed. Okay, so it canceled here. Multiplied both sides by the radius of Phobos cubed. And then divided both sides by the period of Phobos squared. And then I take the cube root to get rid of the cubed. Basically, I just cross-multiplied everything in order to get radius of Deimos on top. Yeah. Okay, so when we plug all of that in, okay, so we have the period of, okay, so we need cube root here. Okay, and we have the period of Deimos, which is 1.262 squared times the radius of Phobos's orbit, which is 9,378, and that has to be cubed, okay, divided by the period of Phobos, okay, which is 0.3189, and that's squared. All right, so we're getting that the orbital radius of Phobos is 23,462.8 kilometers, okay, because it's got to match the units that they gave me for the radius of Phobos's orbit. Okay. All right, everybody with me on that? All right, so quick review here. Advantages of using Kepler's law of periods. Easier, smaller numbers to deal with. Less manipulation to deal with. Downside of Kepler's law of periods, you have to have just the right information to use it, and rarely are you given just the right information. It will come from time to time, okay, but not always. What way will always solve a satellite motion question for you? Yeah, FC equals FG. Anytime something is orbiting something else, this formula will always work. It is universal. It does, you'll always have the right information to use that formula, right? But you won't always have the right information to use Kepler's law of periods, okay? The 2 objects that you use have to orbit the same central point, which basically means for a satellite orbiting the Earth, we're not going to be using this, okay? Why can't we use Kepler's law of periods for a satellite orbiting the Earth? What else orbits the Earth? Big white thing. Yeah, the moon. No, that doesn't orbit the Earth. We orbit that. Okay, and it's yellow. Okay, so the moon also orbits the Earth. Is the period of the moon on your formula sheet? It is not. There's a reason for that. If it was, you'd be able to use Kepler's law of periods for every satellite motion question. So we on purpose keep it off of there, okay? That you actually have to use FC equals FG. All right. So I don't want you to get confused, guys, because here's what I see people do with satellite motion problems. They're like, oh, I so want to use Kepler's law because it's so much easier. So they go, all right, this satellite's orbiting the Earth. So I'm going to take the period of the satellite squared, and I'm going to put that over the radius of the satellite cubed, and I'm going to set that equal to the period of the Earth squared over the radius of the Earth cubed. So Earth orbits Earth then. That's what you're saying when you do that. Not only will you get absolutely ridiculous numbers, okay, you will do it wrong. And that sucks because then you won't get any marks. Okay, so, okay, yeah, Kepler's nice, but you got to have just the right situation to use it. Okay, that'll come up sometimes, and then it's perfectly fine to use Kepler's law of periods. Okay, now we got to talk about gravitational fields. Okay. All right, so fields are not something we've talked about yet in this course. Okay, some forces that we deal with are field forces. That means they don't have to be in contact with an object, like in physical contact with it, to exert a force on it. All right, gravity is a field force. Friction is a contact force. There's no field of friction around an object. Okay, there just isn't. All right. Same with normal force. Normal force is a contact force. Okay, we know that because if you're not touching the object, it can't push back on you. Okay, so most of the forces we've dealt with are contact forces, but gravity is different because gravity is generated by mass. It can exert its influence in a large area around that mass. Okay, the larger the mass, the greater the strength of the field. Okay, but the field strength is affected by the same things that the force of gravity is affected by. Okay? So the force of gravity, according to Newton, is affected by the mass of the two objects and how far apart they are. Okay? Gravitational field strength is more a measure of the acceleration of the smaller object towards the bigger object. Okay, that's what field strength is measuring. It's the acceleration or the rate of attraction between these two objects, right? And that's always measured as the big one on the small one. So really, what gravitational field strength is doing is saying this. mg equals big G times mass 1 times mass 2 over r squared. That should be true, right? They're both force of gravity. But what gravitational field strength wants to calculate is this. Gravitational field strength is acceleration due to gravity. So if I manipulate this formula to find little g, what happens to this mass? It cancels off. Okay? And is it the bigger or the smaller of the two masses? It's the smaller of the two. Because remember, the rate of gravitational attraction is not dependent on mass. All things fall towards the Earth at the same rate. Okay, that's true for anything other than the Earth. Okay, if we're talking about the sun, it's true for the sun. Okay, it's true for any other large object that generates a gravitational field. At a certain distance, you will fall at this rate. At this distance, you will fall at this rate, regardless of your mass. That's why the small mass cancels. So this is the formula that's on your formula sheet for gravitational field strength. Okay, so gravitational field strength is not the same as the force of gravity. Okay, the force of gravity is how hard are the two objects being pulled together? What's the mutual attraction between them? Field strength is how quickly are they being attracted to each other? All right, so one's a force and one's an acceleration. Everybody follow the difference there. You really need to understand the difference there because every year on the unit exam for this unit, I put a gravitational field strength question on there. And what I do is I write whatever the situation is, and then I write calculate in bold-faced, italicized, underlined font, sometimes in bigger point font as well. I write on there, calculate the gravitational field strength experienced by this object. And 1/3 of the people still calculate the force of gravity. Even though I specifically say calculate this, and I make a point of making it obvious, people still calculate the force of gravity. I give this speech every single time I teach this lesson. In 18 years, 2 classes have proven me wrong. In 18 years. 2 classes have had less than 30% of people do that question wrong. One class was 27% and the other was 20%. Okay? There's still people that do it wrong. Okay? But really it should be a freebie because it tells you, use this formula. You don't have to manipulate it, just use it and you'll get the answer right. Okay? But people just calculate the force of gravity for whatever reason, even though it says not to. All right? Everybody with me there? I've given you a big, giant, juicy freaking hint for next week's test. Okay? Be ready for it. All right, so Earth has a gravitational field. It's big, even though the Earth is, in terms of mass, relatively small compared to other things in the solar system. Earth's gravitational field is big. But obviously, the further away from Earth you get, the strength of that field decreases exponentially, according to the formula we just looked at. Okay? That said, lots of things are trapped within the Earth's gravitational field, which we also sometimes refer to as a gravity well, okay? Because you could fall into it, okay? Because it's gravity. So the moon is one of the objects that's trapped within the Earth's gravitational field. By that same reasoning, Earth is also within the moon's gravitational field. Can we see the effects of the moon's gravitational field? We can, because the Earth wobbles and because we have tides. Okay, the tides are the influence of the moon's gravitational field pulling the fluid water on the Earth's surface towards itself. Okay, that's what causes the tides. Okay, the moon pulls the entire ocean towards itself, which is a pretty spectacular feat when you consider how far away the moon is and how big the ocean is. Okay, it can pull all that water towards itself, okay, due to its gravitational field. So there's this interaction between the two. Okay, everybody with me there? So this is a big deal if you're sending people to the moon, because you're going to have this ship that's going to leave the Earth and be in Earth's gravitational field, but it's also going to be in the moon's gravitational field. Now, which one is stronger? Okay, Earth's is stronger, depending on where you are. Okay, there's a tipping point, and NASA, whoever's sending the ship to the moon, needs to know where that tipping point is, because if they're continuing to accelerate when they get into the point where the field of the moon is greater, the rocket will accelerate away rapidly, and we don't want that. We want to slow down as we approach the moon, okay, and land on its surface or go into orbit around it safely. Okay, so we have to know where that tipping point is. Gravitational field strength is dependent, again, exponentially on radius, okay, or separation distance. Okay, so Michael Faraday is the guy that first discovered this idea of fields, okay, but he discovered it using electricity and magnetism, okay, something that we still use today. In fact, we use a ton of Faraday's discoveries to this day. How many of you use a wireless charger for your phone? Okay, not many of you. You shouldn't. It's really actually quite inefficient, but it works, okay? And it was Faraday who discovered that you could induce an electrical current using a magnetic field. So that's what a wireless charger does. It has a magnetic field that it generates, and if you set your phone on top of it, that can make the electrons in the battery of your phone move in such a way as to charge the battery, okay, without actually having to plug it in. It just induces a current because of the magnetic field that's surrounding the wireless charger. Okay? They do that now in a few cities to charge electric cars as well. Okay? There's certain parking spots, and you just park over top of this big plate, and the plate generates a magnetic field that charges the battery, okay, without actually having to plug it in, right? Which is nice because people have been stealing the cords. Okay, like at the charging stations, people will cut the cords and steal the cords for all the copper. Apparently they can sell the copper or something, I don't know. Okay? But they've been stealing the cords from all the electric vehicle charging stations. Okay, so they want to have these wireless ones because they're harder to steal. You'd have to dig up the street. So, it's hard to make an effective getaway when you're using a jackhammer. All right, so we've got this idea of the field. What Faraday discovered is that the magnetic effects of an object, okay, like a magnet, were not localized. Okay, there was a magnetic effect that went away from the magnet or from the electric field or whatever, okay, he discovered that there was an area of influence that this object or thing could have on other objects. Okay, the simplest demonstration of that you probably saw when you were in elementary school. They take a magnet and they put iron filings around it, and all the iron filings align, okay, with the magnetic field around the bar magnet. It looks something like this. Okay, so if you have a bar magnet, okay, it generates a magnetic field that has two halves, and all the iron filings will align, okay, with that field, and you can actually see the shape of the field. The Earth has a magnetic field that's exactly the same shape. It's really just a big giant bar magnet. Okay, and so we get this area of influence. Gravity is the same. Now, of all the field forces, gravity is the weakest. Okay, in terms of like per kilogram, magnetic fields and electric fields are way stronger. The difference is that they don't extend out nearly as far because they don't deal with as much mass as gravity does. Because gravity deals with mass and there's so much matter in the universe, gravity is what governs all the workings of the universe in terms of movement. Okay, all right, so the field acts on the second body at whatever location it's at. So if the moon is here, okay, the gravitational acceleration towards the Earth is a certain value. Were the moon closer, then that value would be larger. Okay, and so on and so on. All right, and same for the reverse. Okay, the effect of the moon's gravitational field would be greater if it was closer to the Earth. Okay, and we see that actually because tides aren't always the same. Okay, you can have like really high tides one week, and then the next week the tides are much lower at high tide. Okay, and that's because the moon's orbit isn't perfectly circular. Okay, there are times where the moon is closer to the Earth than others, and when it is, we get higher tides than normal. When it's at apogee, further away, okay, then we get lower high tides than we usually do. Right, and that's easily measurable, okay, on Earth. Okay, so the idea of the field was important because it told us essentially how some things work without being in contact with each other, but it also made the idea of having to have like invisible threads and things like that connecting things obsolete. Okay, because for a long time, all the field forces were explained by, well, gravity is this series of invisible ropes that you can't see or feel or touch that are connecting objects and they're pulling them together. Okay, because that's how everyone made everything. Okay, I mean, heat was a fluid for a long time, an invisible fluid that you couldn't see that went from a hot object to a cold object. Okay, we had to come up with these magical ways for things to work until we found out how they actually worked. Okay, so it made this idea of a force acting over great distances using invisible threads unnecessary. Okay, which was important. All right, so to find the strength of the gravitational field, okay, you place a small body of known mass in the field and measure the force on it. Okay, then we can define the field strength, which is the rate of attraction, okay, by dividing that force by the mass, which is what we did just a minute ago when we said m times g equals big G times mass 1 times mass 2 over r squared. Okay, essentially what we did is we took the force of gravity, this, divided it by mass, okay, and we were left with our formula for gravitational field strength. Everybody with me there? Okay, so that's what we did. Okay, so the field strength is numerically equal to the acceleration due to gravity. We actually get different units. Okay, if we do that calculation there where we have big G times mass 1 over r squared, the units we get are newtons per kilogram. But if we look at that a little further, what are the units for a newton? Newton's mass times acceleration. So the units for a newton are kilogram meters per second squared. All right, so I got kilogram meters per second squared, and I'm dividing that by kilograms. I'm left with meters per second squared. So a newton per kilogram and a meter per second squared are the same thing. Okay, so it doesn't matter which unit you use for gravitational field strength, it's right. Okay. All right, what this diagram here, guys, is showing is the gravitational field strength or the gravitational field alignment surrounding the Earth. Okay, so here's the Earth, and this is the moon here. All right, so you can see that on this side of the Earth, the lines, the arrows are all pretty linear. They all point directly towards the center of the Earth. Right? But as we start getting closer to the side of the Earth the moon is on, we see that the direction of those arrows and the magnitude of those arrows starts to change. Okay? They start to get skewed or pulled sort of in the direction of the moon. Okay? So if we're traveling along this line here, we have to know that the gravitational field strength is going to change, and there is going to be a balance point where there will be no acceleration. Okay? We'll be equally attracted to both the moon and the Earth at that circled point because their gravitational fields will balance at that one point. Right? Okay, we get past that, then we'll be attracted to the moon. And you can notice that obviously the field strength lines pointing towards the moon are much smaller than the field strength lines pointing to the Earth at the same distance. That's again because the Earth is more massive. Okay? It generates a stronger gravitational field. Okay, so again, there's kind of the field strength of the Earth. Okay, when we're close to the Earth, the gravitational field strength is large. When we're further away from the Earth, the gravitational field strength is quite a bit smaller. Okay. All right. So we're going to do a couple of examples of that. They're not hard questions. Okay, and then we'll see where we're at. All right, so we want to calculate for this one here the magnitude of the gravitational acceleration of an object on the equator of the surface of the Earth and on the surface of the moon. Okay. And then we'll determine their ratio, so how many times greater it is on the moon than the Earth. All right, so we're not going to use their numbers, we'll use our numbers. Okay, so we'll just forget about that. All right, I want to calculate the gravitational acceleration or field strength on the Earth at the equator. So that's going to be big G, okay, times the mass of the Earth over r squared. Okay, when I plug in my numbers then, that's going to be 6.67 times 10 to the minus 11 times 5.98 times 10 to the 24, mass of the Earth, divided by 6.37 times 10 to the 6 squared, okay, radius of the Earth. Everybody all right with what I've done there? What number should I get here? I should get around 9.81. I'm probably not going to get exactly 9.81, but I should get around that, because obviously at the equator, gravitational acceleration is a little less than it would be on average, right? Because that's the furthest away from the center of the Earth we are. Right? Now, we're actually using here the average radius of the Earth, so we might get around 9.81 when we do this. All right, so I'm getting 9. Whoa. Oh, I missed a 24 here. Missed a number. No wonder that came out really, really, really small. All right, so I'm getting 9.83, okay, which is a little big for standing at the equator, but that's because we use the average Earth radius and not the equatorial Earth radius. Okay. Everyone with me on how that worked? Okay, so that's the value we got for Earth at the equator. Okay, if I want to do this for the moon, then I have to use the moon's numbers. All right, so I'll say G on the moon equals 6.67 times 10 to the minus 11 times 7.36 times 10 to the 22, okay, mass of the moon, and then the radius of the moon. Did we have that on our formula sheet? We don't? Okay, we'll use theirs. Radius of the moon, Earth's moon, 1.74 times 10 to the 6. Squared. Whoop. Okay, so I'm getting 1.62 meters per second squared for the gravitational acceleration there. Okay, and then they wanted us to calculate the ratio between them, so 9.83 divided by 1.62, about 6.1 times. Okay, so you weigh about 1/6 on the moon what you would on the Earth. Okay, everyone follow how we use that formula? Okay, it's a lot like the force of gravity formula, except we have one less mass in it. Are you ever going to set this formula equal to anything like you do with the force of gravity formula? Like, are you ever going to say g times 1 mass over r squared equals something, some other formula? No, this is used for one thing and one thing only. It just calculates gravitational field strength. All right. Have you guys try these ones here? Let's make them big enough to see. All right, so for number one, just use the information on our formula sheet there. We can use the Earth's radius and things like that for that one. Okay, so read them carefully because they might have that altitude trick in them. Okay, just in case. And I'll give you a few minutes on 1 and 2 here. Let's see how we do on those. Okay, so let's have a look at number 1 here real quick. All right, so we got a satellite that orbits the Earth at a distance of 3 Earth radii above the Earth's surface. So part A is easy. How many from the Earth's center is it then? 4. Okay, if it's 3 from the Earth's surface, it's 4 Earth radii from the Earth's center. Okay, that'll help us with this calculation here, because if we want to calculate gravitational field strength, we're going to take the gravitational constant multiplied by the mass of the Earth, and then divide it by the radius, or the separation distance, which will be 4 times 6.37 times 10 to the 6 squared. Oh, sorry, need one more bracket there. Okay, that's what we've got to do in order to solve that one. Okay, so we'll have on the top, okay, so we're getting a gravitational acceleration here of 0.614 newtons per kilogram, or meters per second squared, which would seem to make sense. We're 4 Earth radii from the Earth's center. That's quite a long way. Okay, and we know that that distance is exponentially going to affect, okay, the gravitational acceleration. So that's what they got. Well, it's about what they got. They used their numbers, which is why they got a slightly different number than we did. Okay, all right. Try 2 and 3 there, guys. Give you a few minutes on 2 and 3. Same idea. All right, so for question 2, okay, we're looking for the gravitational field strength on the astronaut. What is causing the gravitational field to act on the astronaut? From where? From where? Earth. Okay, so that's what we got to remember. Okay, we don't want to use this 80 kilograms. We're not trying to find the gravitational field strength of the astronaut. We're trying to find the gravitational field strength on the astronaut due to Earth. Okay, so we have little g equals big G times the mass of the Earth over the separation distance of the astronaut to the Earth's center squared. Okay, so when we plug in our numbers here, that's going to be 6.67 times 10 to the minus 11 times 5.98 times 10 to the 24, and then we're going to be dividing that by this, but it has to be in meters because it's in kilometers here. It is from the Earth's center, so all I have to do is change the exponent. Whoop, not times 10 to the 6 squared. That's not supposed to be 6. It's supposed to be a 2. Okay, squared, and then we should get around the same answer that they have there. Right, it'll be slightly different because they use a different number for radius and Earth's mass. Right. All right, so we're getting 0.38 now. That's what they're getting, 0.389 newtons per kilogram or meters per second squared. Okay, now what changes in that calculation for part B? Right, the mass of the Earth changes to the mass of the Moon. Everything else remains the same. So if you just take your previous entry there and then go up and edit the mass, okay, so now it's going to be 7.36 times 10 to the 22. Okay, and then do it. We get a much, much smaller number, okay, because obviously the Moon has a much smaller gravitational field. Okay, everybody with me on that one? Right? Where did I lose you? You're giving the screen a dirty look. Yeah. Oh, okay. Okay, how many people are done number 3? Okay, I'll give you a couple more minutes on number 3, and then we'll walk through that one as well. Okay, the purpose of number 3 is to make sure you are reading the question carefully. Everything we've talked about today has been about gravitational field strength. Then what does number 3 ask you to calculate? Gravitational force. Okay, so all you're doing with number 3 is you're doing a Newton's universal law of gravitation calculation, where now you do need both masses. Okay, it's asking for gravitational force, not gravitational field strength, which are two very different things. Okay, so when we do this one, we're just plugging in 6.67 times 10 to the minus 11 times 5.98 times 10 to the 24. Okay, and then the mass of the satellites, or sorry, the mass of the astronauts, 70 kilograms. Okay, and then we're dividing that by 6.6 times the Earth's radius. Okay, and when we do that, we should get around 16 newtons towards the Earth's center. Okay, everybody follow me there. All right, so read the question carefully. Remember, on the test, I will have it in bold-faced, italicized, and underlined in slightly larger font, okay, so that you have no excuse to not get the question right, because I want you to get the question right. I want to be proved wrong about this 30% rule, okay? Desperately want to be proved wrong about it, okay, because I'm tired of it. Okay, question A is a question I absolutely love, and I have put it on this test before. $60 kilograms? Oh, in the picture you mean? Yeah, they do look very big in that picture. They obviously aren't very dense because they only weigh 60 kilograms, but they're the size of a planet. They're out in space. Okay, what's the mass of a 60 kilogram student on Mars? 60 kilograms. You'd be surprised how often I don't get that answer when I ask that question. Okay, if I make it a multiple choice question, I make sure to put on the weight of the person on Mars and the Earth, and people calculate that, and then they're like, oh, I'm so smart, it's one of the answers. Except it's the wrong answer. I know how you might do that question wrong, and I'm going to do it that way, and I'm going to put the answer on there. Yeah, I'm that mean. So are the diploma exam people, okay? They're that mean too. They figure out every possible way you'll do the question wrong, do it that way, and put those answers on there. Then you get this false sense of security when you're writing the test, okay? All right. Now, the second part asks you to calculate the student's weight. So is that gravitational field strength or force of gravity? It's force of gravity. Weight is the force of gravity. Okay, so all this question is asking. Remember the difference between the two. Mass and weight are different. Okay, gonna have you guys try a couple of the ones from our workbook here. Okay, just a couple. Okay, so questions are the same thing we've been working on. Just give them a try. All right, off you go.